Hello students. Now we are going to see what is error of a product or quotient. Okay. So when two physical quantities are getting multiplied or divided, we will see what exactly is the combination of error in that case. Okay. So here you have Z which is dependent on A and B, and both A and B are getting multiplied to each other. So here I can simply write that A is basically A plus minus of delta A, right? Error in A. Similarly, B is going to be equal to B plus minus of delta B. This is the error in B. When they are getting combined, the final quantity which is Z, that is going to have some error as well, right? Z plus minus delta Z, alright, and this is going to be equal to the multiplication of A and B, and A and B are these. So just multiply them. So here you have A plus minus, right, A plus minus delta A, okay, multiplied by B plus minus delta B, okay. So this is the final value. Now if you do the multiplication here, this is going to be equal to, right, here you have A plus minus delta A, B plus minus delta B. So basically AB, right, AB multiplied by, okay, so this is going to be equal to plus minus A delta B, and then delta A, I can write this as plus minus B delta A, and then plus minus of delta A delta B, delta A delta B, okay. So here you have these 1, 2, 3, 4, these 4 terms which are getting multiplied like this, okay. Here once again you had Z plus minus delta Z, okay. Now the next step, just to simplify this, what I can do is I can take AB common from this equation, from this side of the term which is on RHS, and I can take Z common from LHS, okay. So if I do that, let's see what we are going to get here, okay. Here if I take Z common, I'll get Z outside, and eventually this is going to be equal to 1 plus minus delta Z upon Z, okay. Look at this. If you just multiply this again, once again, this is going to be equal to Z, and then Z and Z here will get cancelled, and eventually you get the same equation, okay. So I have taken Z common like this, alright. Now I am going to take AB common from this whole term, alright. So let's see what we are going to get is AB is common here, so AB, and then the remaining thing, this AB is taken out, so that means here I will have 1, and then 1 plus minus A delta B, okay. So A, B both are taken common, so A is out, but here there is not B, so I'll have to divide this with B. So this is going to be equal to delta B upon B plus minus delta A upon A plus minus, here there is neither A nor B, so therefore this is going to be equal to plus minus delta A upon A. Can I write it like this, delta A upon A multiplied by delta B upon B, okay. So these two are getting like this, okay. So here what else can we do? Look at this, AB, and then there is Z. What is this? Let Z is equal to AB. If I say that this is the equation 1, then from this equation 1, both are equal to each other. Here Z, here AB, both are in multiplication. Can I cancel them out? Z and AB, right? From equation 1. So once I cancel that out, here I still have here 1 plus delta Z on all of this, and then 1 plus minus all of this. So here 1 and 1 will also get cancelled, okay. Now upon simplification, let's see what is it that we are going to find out, okay. So here upon simplification, you can clearly see that I'm going to have delta Z upon Z, which is equal to delta B upon B plus minus, right, this one is also plus minus delta B upon B plus minus delta A upon A, and then plus minus of delta A upon A into delta B divided by B, okay. So this is the equation that you're going to get. Now in this case, first of all, look at this, this is delta Z upon Z, Does this look familiar to you? Yes, this is the relative error in Z. So the relative error in Z is going to be equal to plus minus delta B upon B. This is relative error in B. The physical quantity B, it's relative error. The physical quantity A, it's relative error. Okay. And then this is just the multiplication of the relative errors of A and B. Now, in this case, let's simplify this further. Here you will see that this is A and B, right? These two are getting multiplied. Now, in this case, delta A and delta B, both are errors which are very, very small values. Those are usually very small values, and when they get multiplied, they still get even more smaller. And here, A and B, they are substantially larger. They are very large as compared to delta A and delta B. And when they get multiplied, they become even larger values. As a result, if I consider the multiplication of this delta A upon A multiplied by delta B upon B, this is getting very, very close to 0. It's very small value. So this is negligible. So I can simply say that this will this value can be neglected. Why? Because delta A delta B upon AB is very, very less than 1. Okay, it's a very small value. This is approximately to 0 itself. So I'm just neglecting this. Therefore, the final value that I'm going to get is delta Z upon Z, which is equal to plus minus of delta B upon B, which is once again plus minus delta A upon A. Okay. If I want to get to the maximum error possible in this case, remember maximum relative error possible in this case, that is going to be equal to delta Z upon Z, which is equal to, here I'm just replacing these two, so delta A upon A plus delta B upon B. This is the equation that we have. Okay. So delta Z upon Z, which is the relative error in physical quantity Z, is going to be equal to relative error in A plus relative error in B. That's the equation that you get. So from this, we can simply say that the rule that we have is when two quantities are multiplied or they can be divided, in that case, the relative error in the result is the sum of their relative errors in the multipliers. Therefore, all you need to do is, if they are getting multiplied or divided, all you need to do is just calculate the relative error of the result as the sum of the relative errors in each of the individual multipliers. So here, if this was A and B, if let's say this is AB divided by C, even in that case, this is AB then divided by C, what you're going to get is, here you will have plus of delta C upon C. That's it. It doesn't matter that these two are getting multiplied or divided. Whatever there is a new term, all you need to do is just add its relative error, and the overall summation will give you the relative error of the new physical quantity that was said. Okay. So this is the combination of the error of a product or quotient. Okay. I hope you understood. So now we are going to learn about the significant figures. Okay. So see, up to this point, we know that there is always some error in the measurements. Whenever you measure anything, there is some errors. Therefore, the reported result of the measurement will have reliable reading as well as some digits with a level of uncertainty. That means those digits might not matter that much, and apart from that, they have a very uncertain value. The reliable digits plus the first uncertain digit is known as the significant figures or digits. Okay, we'll try to understand this with an example. Here you can clearly see that I want to measure the length of this pencil. Okay, now this pencil is kept at the 0 reading right here, and let's say this is a centimeter scale. Okay, so if this is a centimeter scale, 0 centimeter, 1 centimeter, and then you have 2 centimeter. In this device, you can clearly see 1, 2, 3, 4, 5. So basically there are 10 readings between any two. So this one is going to be the least value is going to be of 0.1 centimeter. Okay, so here up to from this point to this point is 1 centimeter, and a very small reading, basically the least reading that this scale can give you with accuracy, with better accuracy and precision, that is going to be 0.1 centimeter. Apart from that, the value, whatever value that you're getting, is not going to be certain enough. So here you can clearly see the final tip of this pencil ends up to this point, somewhere here. So you can clearly see that this is lying somewhere in between these values and this value. So this is basically 1, 2, 3. So this one is 1.3 and this reading is 1.4. So that means the tip of the pencil, or basically the whole length of the pencil, is somewhere between 1.3 and 1.4. It's not exactly 1.3 and it's not even exactly 1.4. It's in the middle. So we can clearly say that in this case, the final reading is going to be 1.3. Now children, up to 1.3, the length of the pencil is obviously a little bit, teeny tiny bit larger than 1.3, but we are totally sure, we are 100% sure that in this case, the value is 1.3, okay? But obviously it's a little bit larger than that, so maybe you just take a guess that probably it's somewhere in the middle itself. So let's say this is 1.35 centimeter. But in this case, how many figures? First of all, in this value, how many figures are there? Or how many digits are there? There are 3 digits. Okay. So the total number of digits that you have is 3. When you have 3 digits, but in that case, you're 100% sure, you're certain about 2 digits. And the third digit is uncertain. This one is uncertain. Now, in this case, I can say that the number of significant figures or significant digits which we are certain about, okay, and with plus 1, okay, plus the first uncertain digit is known as significant figures. So here we can say that the total number of significant figures is 3, in which these two are, we are 100% certain, and then 5, this is uncertain. Okay. So like this, we understand about the certainty and uncertainty of any value in any measurement. Okay. Some values are 100% certain. That means in this case, there is no doubt about that. But later on, some of the values are a bit uncertain. And we need to understand that. We have to have the understanding for those values so that we can get better and better at different measurements. Okay. So, but the thing is, see, here you can clearly see more the significant figures. Okay. More is the number of significant figures or digits in any value, more accurate is the measurement, right? So for example, this was the scale, but now I'm not using this scale, instead I'm using a vernier caliper. So in a vernier caliper, I'll get even more digits. After this decimal point, I'll get maybe 1 or 2 more decimals. If I'm using, let's say, another better precision instrument, that can give me much more better results. So more is the number of significant figures, more is the accuracy of the measurement. Change in units does not change the number of significant figures. This is one of the rules actually, and I'll give you some examples as well. But as of now, just keep in mind that the change in units, if you're changing the units, for example, here this is 1.35 centimeter. If I'm about to change this into meters or kilometers, the number of significant figures must not change. They will always remain the same. Okay. So we'll talk about this later. As of now, we have the significant rules. Later on, we are going to see what are the different rules so that you can understand and calculate the number of significant figures in any given number. Okay, so if any digit or any measurement is given to you, you have to be understandable and you have to know that how you can take the number of significant figures in that value. Okay, so we'll do the rules of these significant figures later on. Thank you. Now we will begin with the rules to calculate the significant figures. There are different significant figures, and how do you calculate the number of significant figures in any digit? Okay, so let us look at the first rule, which is all non-zero digits are significant. So for example, here 2, 3, 4, 1. If this is a number. Here the number of significant figures will be 1, 2, 3, 4. So this basically has 4 significant figures. Alright. The second rule is all zeros between two non-zero digit, these are also known as the trapped zeros, are significant no matter where the decimal point is. Okay, so this is your second rule. For example, here look at this 1.008. Now in this case, this is a non-zero digit, 8 is also a non-zero digit, and these are the trapped zeros. And in this case, the trapped zeros will be considered as the significant figure. So how many number of significant figures are there? 1, 2, 3, 4, right? In this case, tell me how many number of significant figures? 1, 2, 3. It doesn't matter where the decimal point is. In all these cases, if the zeros are trapped between two non-zero digits, those will be counted as significant figures. Look at this. 1, 2, 3, 4, 5, 6, 7. These will be 7 significant figures. Okay. The next rule is initial zeros are never significant. And in this case, even if there is a decimal point, after the decimal point, that will not be taken as significant. Here, look at this. How many significant figures are there? 0.001, one significant figure. 0.215, 3. 0.045, here this will again be 2, right? 2. And then 0.0903, these will be 4 significant figures. Alright. Finally, we have trailing zeros are significant if they appear after the decimal. Now, when you put a decimal point and after that there are trailing zeros, those zeros are very much significant. Okay. In this case, look at this 2.00. So 2.00, is it one significant figure or is it 3 significant figures? By looking at this rule, which is trailing zeros are significant if they appear after the decimal. According to this rule, in this case, there will be 3 significant figures. Okay. Now look at the second one, 3.120. Now, if this rule was not there, we would have said that this is basically 3 significant figure, but because of this, we'll say there are 4 significant figures, right? The trailing zeros after the decimal are significant. Okay. Here look at this 0.003020. Now what should we do? See, in this case 0.00 in the, after this, these two zeros can be ignored, but the trailing zero, this will not be ignored. So here in total the number of significant figures are 1, 2, 3, 4. Once again 4 significant figures. Okay. Look at this 200. There is no decimal point in 200. Okay. So this means in this case there is only 1 significant figures. What about this 1800? For 1800 there are 2 significant figures. Okay. There is no decimal point, and in this case when there is a trailing zero but there is no decimal point, in that case this will not be considered as a significant figure. But if you put a decimal point over there, those zeros will be considered as significant figure. Okay. Let us take a look at this one. In exponential notation, the numerical portion gives the number of significant figure. So when you are writing the numbers in exponential form, and this will be used heavily in physics, alright, when we deal with very large numbers or very small numbers. In that case, whatever this quantity is, this one gives you the number of significant figures. Here 10 raised to the power 3 is not counted as any significant figure. Okay, so basically this works usually as the conversion unit, and the significant figure is basically this one. Okay. So look at this. How many significant figures in the first example? Quickly do this. 2.3. That means in this case, this will be 2 significant figures. Okay. Look at this. 2760.00 and 10 raised to the power 3. Now see, in this case, once I have a decimal point here, that means all these zeros will be considered. And remember, after the decimal point, the trailing zeros are considered as the significant figure. So therefore here 1, 2, 3, 4, 5, 6. There will be 6 significant figures. What about this? 276,000. In this case, there are only 3 significant figures. Why? Because there is no decimal point here. Okay. What about this 900? The same rule. In this case, 1 significant figure. 9 into 10 raised to the power 2, once again 1 significant figure. Okay, I have not put any decimal point over there, that is why one significant figure. Let's say I write this as 9.0 multiplied by 10 raised to the power 2. Now this will have 2 significant figures. Okay, so here there will be 2 significant figures. Now let us look at the next rule, which is pure numbers of constant have infinite significant figures. Pure numbers or constant. What I mean by that is, for example, here radius is basically diameter divided by 2. So whatever diameter that you calculate, that will have some significant figure, but again the overall value is getting divided by half. Now this half is an absolute value. This is a constant. Okay. So for example, here half can be written as 0.5. Okay. Now because this is a constant, after this I can keep on putting further trailing zeros after the decimal point. And remember the rule, after the decimal point, whatever number of trailing zeros are there, they will be considered as the significant figure. Now because this is a constant, I can keep on adding like this, and eventually I will have infinite significant figures. This basically tells us that these constants are 100% sure, right? Keep in mind that the significant figures, they have to deal with the certainty or uncertainty of any digit, anything that you're measuring. Now, when something is constant, that means that object or that measurement simply cannot change. So therefore, they have infinite number of significant figures. Okay, 2 pi r in this case as well. Here 2 is a constant, right? So I can simply write 2 as 2.000000. The value does not change, but if I keep on adding zeros here, eventually I'm going to have infinite number of significant figures. Okay, so that's what this means. Finally, while changing units, the number of significant figures remain the same. Okay, from this rule, a lot of questions also come in. Okay, so I'll give you an example as well. But here, the same thing they're telling is, whenever you're changing the number of units, or basically any units are getting changed, let's say from meter to kilometer. In that case, whatever number of significant figure there were in meter, when you convert that into kilometer, you need to make sure that the number of significant figures are same. Number of significant figures should not change. For example, here look at this, 1.5 meter can be written as 150 centimeter, yes or no? Yes. Now in this case, this digit will have 2 significant figures, right? What about 150 centimeter? 2 significant figures. Okay. So there is no problem in this. This is totally correct. What about this? 2 kilometer and 2000 meter. The conversion is correct. So mathematically there's not much problem here. But in perspective of significant figures, how many significant figures are there? 2.0 kilometer. Remember, after decimal, the trailing zeros are significant. Therefore, this 2.0 kilometer will be taken as 2 significant figures. Okay. But what about 2000 meter? For 2000 meter, here there is no decimal point. That means the number of significant figure in this case is 1. So in perspective of significant figures, this equation is wrong, because there are 2 significant figures over here and there is only 1 significant figure over on the right hand side. Okay, so make sure that whenever you're converting the units or you're changing the units, the number of significant figures must not change. So here look at this example, 8.0 kilometer can also be written as. Now before we move on to this, to these 4 options, let's quickly see that this is 8 kilometer, right? And we know that 1 kilometer will have 1000 meter. 8 kilometer is going to have 8,000 meter. Okay. So just by looking at the numbers, I can simply say that 8 kilometer, 8,000 meter. This also seems correct. Here, 8.0 into 10 raised to the power 3. I can easily write this as 8 into 10 raised to the power 3 meter. Yes or no? So this also seems a bit correct. Here, 0.8 into 10 raised to the power 4. Look at this. This is 10 raised to the power 3. If you move one decimal to the left, here I'll have to add one more power to the 10. So I can simply write this as 0.8 multiplied by 10 raised to the power 4. So this also seems correct. Now in this case, we need to look it in the perspective of significant figures. So first of all, how many significant figures are there in the question? 8.0 kilometers. There are two significant figures. How many significant figures are here? Look at this. 8,000 meters. That means only one significant figure. Okay. 8.0 into 10 raised to the power 3 meter. Here there are two significant figures. Okay. 0.8 into 10 to the 4. Once again, only one significant figure. Remember, after decimal, the trailing zeros are considered as significant. This zero is insignificant. Okay. So therefore, I have only one significant figure over here. So this means totally all of the above, this answer is incorrect. One significant figure, incorrect. One significant figure, incorrect. The correct answer is option B. Okay. 8.0 into 10 raised to the power 3 meter. So the scientific method to convert 8.0 kilometer into meter, that is 8.0 into 10 raised to the power 3 meters. Now, to a layman, this might not seem that big of a deal, but when we are dealing with significant figures, it's very important and crucial. Okay, so there you have it, the basic rules of significant figures, and these are the rules which you will be using to identify that any measurement or any number of digits, how many significant figures are there. Okay, thank you.